This screencast is about transformations to quadratic functions, and we're going to look at something called a vertex form that's going to help us be able to do that. When we're using the vertex form, in the form y equals a times the quantity x minus h squared plus k. Now, h and k are variables that define the vertex of the quadratic. This makes it actually very useful for identifying the vertex. This helps us to quickly determine the intercept and actually quickly determine how the function is transformed from the parent function of y equals x squared. So the vertex occurs at the coordinates h comma k. So we can look at the number inside the parentheses and the number outside the parentheses and determine the x and y coordinates of the vertex, which is often the most important point of a quadratic because it represents either the minimum for an upward-facing parabola or the maximum for a downward-facing parabola. So we're going to cover how to go back and forth between the vertex form to the standard form. And we do that actually by completing the square. And if you need help with completing the square, look at a previous screencast. We go over how to do that. But essentially, we're going to take that standard form and we're going to break it into two parts. The ax squared plus bx, we're going to complete the square and add a constant that makes that a perfect square. And then we'll then subtract that constant from the other part so that we don't actually change the algebraic truth of the equation. So let's look at what these transformations actually do. So changing the h, that number that's inside the x minus h term in vertex form, it actually does a translation left or right. If h is positive, it's going to be shifting it to the right. In other words, if we have x minus some number. If we have an x plus h, then h is actually negative because it's in the form x minus h. So if we have an x plus h, that means h is a negative number, and that is a shift to the left. The k number is kind of easier to work with. It's on the outside there. That's shifting the output up or down. It is translating the parabola from the parent function up or down the appropriate number. If k is positive, it shifts it up. If there's a negative number there, it shifts it down. The a number, if it's positive, as we already know, reflects the function. So if it's positive, it's upward facing. If it's negative, the a term is negative, it's downward facing. So it's reflected about the x-axis. And finally, the last transformation that occurs that we can see is called dilation. If the absolute value of the a term is greater than 1, then it's going to stretch the graph out, like this red graph here. The red graph is vertically stretched. If you can imagine somebody pulling it up and down from the top and bottom, that's what it would look like. The blue is the parent function, y equals x squared. If the absolute value of the a term is between 0 and 1, but not including those numbers, then it's going to compress it. In other words, if we kind of pushed on the graph from the top and the bottom, it would compress it. So that's what transformations of quadratic functions do. It's very, very similar to the other transformations we talked about with parent functions. You can look at that in a previous screencast. So let's look at an example of converting something to vertex form from standard form and then actually describing what that means and how the function looks as compared to the parent function y equals x squared. So we're going to take this function y equals x squared minus 2x plus 4 and convert it to vertex form. First thing we have to look for is it already a perfect square? Because if it is, we can very easily convert it to vertex form. This one isn't. It looks like it might be, but it's not. And so we are going to complete the square. And if you recall from completing the square, we're going to take half that middle number and then square it. So we're going to do 2 divided by 2 squared, which gives us 1. So we're going to finish completing the square by adding the 1, making this parentheses term a complete square on its own. But to keep it algebraically true, if we're going to add 1, we do have to subtract 1 to balance that out. Now that looks like it's making it more complicated, but we can actually factor, after we subtract, we can factor that perfect square into x minus 1, the quantity squared. It's a negative because we have a minus 2x. And then, of course, 4 minus 1 is 3. And so what we've done by completing the square here is turn this into vertex form. Algebraically, both these statements are the same, but sometimes one form is more useful than the other. Again, where the vertex form is super useful is what we're about to do next. And that is actually describing its transformations. So here's our vertex form equation. And we know that because it's in the form x minus h and h is positive, I know that's confusing. It's a positive 1 that's h. That means it's translated 1 to the right. Another way to look at that is if I took the number positive 1 and put it in to x minus 1 squared, I would get a 0. And that's another way to look at it. It is also translated 3 up because this 3 term is the k term on the outside. Positive 3 means 3 up. There is no dilation because the a term, which doesn't even appear because it's algebra, and if there's no number, we assume it to be 1. A equals 1, there is no dilation. It's neither vertically stretched or shrunk. And finally, we know since it's a positive a term, positive 1, it is upward facing. So we know all these things just by looking at the vertex form. And so here's a graph of it, if you were to graph it. The green graph is the parent function y equals x squared. And then the red graph is the graph that we're talking about here. And it is, you'll notice from the original x squared, it's translated to the right 1 and up 3. It is not dilated. It has the same stretch as the original parent function. And it is also upward facing. So all these things are verified in the graph. Let's look at now another example. So let's take y equals negative 3x squared plus minus 18x plus 10, put it into vertex form, analyze the function. Okay, so the first thing we're going to do is we know it's not a perfect square. We're going to go ahead. We do need to factor out the negative 3. Okay, so we can wind up with a 1 term for the a. So if we take a negative 3 out, it becomes negative 3 times quantity x squared plus 6x plus 10. Now we can complete the square on this part right here, the x squared plus 6x. So we're going to divide 6 by 2, and we get 3, and then square that, and we get 9. So we're going to add 9 here, but really, you've got to be really careful. Since the 9 is multiplied by negative 3, we're actually going to, this is really like negative 27. So if we got a negative 27 here, we've got to have a positive 27 to cancel it out. That's because the negative 3 is distributed to the 9. Be super careful with that. Very common source of errors. Okay, and that actually, when you simplify this, it becomes, this factors into x plus 3 quantity squared, because we do have a positive 6x in the middle. And then if we have 10 plus 27, that's where the 37 comes from. And of course, the negative 3 factor is still there. So this is in nice vertex form. Again, it's algebraically equivalent to the standard form, but the vertex form is more useful to us in terms of looking at transformations, which we will now do. So we've got negative 3 times quantity x plus 3 squared plus 37. Well, it's translated 3 to the left. So because a negative 3 will make this 0, this is in the form x minus h quantity squared. And so that's really h negative 3, because then it becomes x minus negative 3. So it's translated 3 to the left. It's translated 37 up, because here's the k term, is positive 37. And it is a 3-time vertical stretch. So this one's going to be really stretched out vertically because the absolute value of a is greater than 1. Now, however, since that is a negative 3, it is downward facing. So those are the things we know just by looking directly at the vertex form. Here's a graph to show you the comparison. So the blue is y equals x squared, parent function of all quadratics. And the red term, the red graph, is the one we're analyzing. So now let's look at an example of taking a graph itself that you're given and then determining a function from it. It's a very useful skill. So we have this parabola on the left, and the first thing we're going to do is identify the vertex. Okay, so the vertex is up here, and then pick any point you want. Ideally, it's going to be something that's very close to an integral point at the corners of the grids. And so I've got a vertex at 1, 3, and I've got another point here, looks like at 0, 1. With those two pieces of information, we can create the vertex form of the equation. So the next thing we're going to do is go ahead and write out the vertex form. Y equals a times quantity x minus h squared plus k. Now that we know the h and k because they represent the 1 and the 3 of these two coordinates, we're going to substitute that in. So we get y equals a times quantity x minus 1 squared, the h, plus 3. The only real unknown here is a, and we have one additional point, 0, 1. So what we're going to do next is go ahead and put the x and y coordinates from 0 and 1 into the x and y of this equation. That's going to help us find the a, which is the only thing we don't know. So when we substitute a 1 for the y and a 0 for the x, be very careful with order in doing this, we can solve for the a term. This is a lot like in slope-intercept form solving for the unknown intercept. Same kind of concept. So algebraically, this becomes 1 equals a times 1, because 0 minus 1 is negative 1 squared, which is positive 1, plus 3. We're going to use the subtraction property of equality and subtract 3 from both sides. And voila, we're going to get that negative 2 equals a. Now all we have to do is write it in that form. And so our equation in vertex form of this graph is y equals negative 2 times quantity x minus 1 squared plus 3. If you needed to turn it into standard form, you would just have to distribute out that x minus 1 quantity squared. So we've looked at transformations of quadratic functions, which are very easily determined from the vertex form, and also how to take a graph of a quadratic and turn it into a quadratic function.